Alright, so tonight I'm going to show you how a simple DC motor works, and if everything works out, give you a demonstration of a simple DC motor like this one working. But first, some background history. So we can trace this kind of rotary DC motor back to 5 different scientists from the mid-1800s. First off, Hans Christian Ørsted, okay, and André Marie Ampère in 1820 proved that an electric current creates a magnetic field, and that statement is what allows these kind of motors to work, because it's by running a current through a loop of wire and that creates the magnetic field, and it's that magnetic field that creates a force that ends up turning the motor and providing the mechanical energy that can be used for really anything that a motor is used in. So a year after they proved that a current produces a magnetic field, British scientist Michael Faraday created the first direct current motor to work in a laboratory setting. And I say to work in a laboratory setting because this wasn't the kind of motor that you could take places or really move outside of a lab. It was basically just a long strand of wire suspended in a tub of mercury and surrounding a magnet. And while it did work to prove that by sending a current through the wire, it would end up rotating through the pan of mercury, a pan of mercury is not exactly the best material to be carting around, so not a very practical motor. It took 10 years for a better design to be created by American scientist Joseph Henry. In 1831, he made the first motor with a simple electromagnet, the same kind of bar magnet that you could find in your science classroom today. And this magnet rotated on an axle instead of being suspended in the air, and was a lot more practical and a lot more portable than Faraday's motor. Unfortunately, this was also a motor that never really left the laboratory setting. But the next year, 1832, English scientist William Sturgeon created the first true rotary DC motor. It was basically just a version of Henry's motor that had been turned on its side, but it was that turning that allowed it to be made portable, and that same basic design is still in DC motors that are built today. So what was that design? The Sturgeon motor had 3 basic parts to it. First, a power source, which in this motor is going to be provided by these 2 batteries. Second, a stator, or a set of permanent magnets that would stay in place while the rotor or the armature rotated around them. That's where you get the rotary motor. And by sending a current from the power source through the wiring and into the rotor, it would produce a force that would create a magnetic field, and that magnetic field would end up turning the rotor and creating a mechanical output. And that works because of something known as Fleming's right-hand rule, first right-hand rule. You may recognize this positioning from your science class, but the basic idea is that the current and the magnetic field that the current produces are always at right angles to one another, and that magnetic field and the force, the net force that it ends up producing, are always at right angles to one another. So if you look at the rotor here, as the current, my thumb here, goes around the wire, it sends out a force that ends up going around the wire in a circular pattern and is always pushing it in the same direction, either forward or backward. Backward. There we go. And like I said, this motor is pretty much a reinterpretation of William Sturgeon's motor. And now let's give it a try. So right now I have it disconnected right here, so it doesn't drain the batteries, but all it should take is to refit that connection like so. Yep, and you can see that as soon as the circuit is completed, the current can start flowing through the wire and it begins to spin. And if we break the circuit, it stops. Now then, there's one more piece of this motor that was not in the original design, but is really useful for modern applications, and that is the potentiometer. It doesn't look like much, but what this knob does is it allows the current that's flowing through the wiring to be changed, to be lowered. So if you lower the current, that ends up lowering the strength of the magnetic field that's around the wire, and that ends up lowering the force that the wire creates, meaning it slows down. So this is not the potentiometer slowing it down, this is just the rotor being finicky. Let's just give that another start. Yeah, come on. There we go. So let's see what happens when I turn the potentiometer down. And you can see that by upping the resistance in the wire, the rotor doesn't have as much current flowing into it and slows down or nearly stops. And if I turn it back up and give it another push, the motor is going at, come on, its original speed. Alright, so that's pretty much it for a basic DC motor. Thanks for watching.